Hi, welcome to this tutorial on problem solving with the combined gas law. Why the combined gas law? Well, it's a whole lot easier than remembering three different gas laws. So, by now, you should know that three things about a gas, a quantity of a gas, are related. Its volume, its temperature, and last but not least, the pressure under which the sample is being kept. Now, there are distinct relationships between all of these factors. For instance, volume and pressure are inversely related, which means when volume goes up, the pressure goes down. It means when the pressure goes up, the volume goes down. That's Boyle's law, if you care. And it's usually expressed as P1V1 equals P2V2. Because if we have a sample of gas at a given pressure and volume, and we change either the volume or the pressure, we can calculate the final volume or pressure because of this relationship. Okay, great, if you want to keep a bunch of gas laws straight. Now, volume and temperature, these two are directly related, which means when volume goes up, temperature goes up. When volume goes down, temperature goes down. This is Charles' law, again, in case you're keeping score at home. So, this is typically expressed as V1 over T1 equals V2 over T2, which means if we have a given volume of gas at a given temperature and we change either its volume or the temperature at which it's being held, but we don't change the pressure, we can compute the final volume or temperature. Now, the one catch to Charles is the temperature absolutely must be in degrees Kelvin. If you are having problems converting from Celsius to Kelvin, please go view my tutorial on Celsius-Kelvin conversions. Okay, so that's Charles' law. Again, fantastic if you want to keep track of three separate gas laws. Okay, the last of our relationships. Pressure and temperature are also directly related. This is Gay-Lussac's law if you're keeping track at home again, which means when temperature goes down, pressure will go down, and when pressure goes up, temperature will go up. It's a direct relationship, often expressed as P1 over T1 equals P2 over T2. Again, fantastic if you want to keep track of a bunch. Same trick applies, however, as did with Charles' law, that temperature must be in Kelvin. Okay, so great, you've got three gas laws. What a pain in the tuchus. Now, here's an easy breezy way, for only $19.99 and a set of Ginsu knives, to never have to remember three separate gas laws again. Ta-da! It's the combined gas law. Really, we've just taken Charles, Boyle's, and Gay-Lussac, smashed them all together, and we get the combined gas law. What this means is that if you only have two of these factors changing, you can just cross out whatever remains constant. Okay, so that's why the combined gas law, in my mind, is so far superior. No more remembering which is which, no more remembering what is what. One equation to rule them all. So again, if all three factors are changing, list your variables, use this, plug in, solve, and then plug in as needed. If only one variable is changing, or two variables are changing, whatever is held constant, you just cancel out. You can cancel out temperature. You can cancel out pressure. You can cancel out volume. It's like magic. Now let's practice one example with the combined gas law. A 44.7 milliliter sample of gas is held at 25 degrees Celsius and 1.47 atms. What would its volume be at STP? Okay, the first thing in solving any problem like this is to list your variables. Okay, so we're given an initial pressure of 1.47 atms, an initial volume of 44.7 milliliters, and an initial temperature of 25 degrees Celsius. Oops, wait, we have a problem. Can we use a temperature that's in Celsius? No, we're going to have to convert that to Kelvin. How do you do that? Remember, just add 273. So we have our initial temperature of 298 degrees Kelvin. Now what about our final conditions? What's our final pressure? What's our final temperature? Obviously, we're looking for our final volume. Well, we're told that we're asked about its volume at STP, which means we have to remember what standard temperature and pressure means. Standard temperature is 0 degrees Celsius, or 273 Kelvin. And standard pressure is 1 atmosphere. That makes the math easy. Okay, now that we have our variables listed and we know what we're going to solve for, it's time to rearrange. It's basic algebra, but you have to rearrange before you plug in. It's helpful to circle the variable that you're solving for. In this case, we'll circle V2, our final volume. We can multiply both sides by T2, and now we can divide both sides by P2, giving us P1 V1 T2 over P2 T1 equals V2. Now it's time to plug in and solve. Okay, that gives us 1.47 ATMs times 44.7 milliliters times 273 degrees Kelvin divided by 1 ATM times 298 Kelvin. As you can see, most of our units are going to cancel out. ATMs will cancel, Kelvins will cancel, leaving us in milliliters, which is the correct units for volume. So I think we've done our rearrangement correctly. Our raw answer is 60.1965 milliliters is our final volume. So, how many sig figs do we get? Well, remember, we have to look back to our givens. Conversion factors are not held against us. And if we look here, well, that 25 is going to be our limiting factor. So, our final answer with sig figs can be expressed one of two ways. As either 60 with a decimal after it milliliters equals V2, or 6.0 times 10 to the first milliliters. I hope this has been helpful. If you have issues with algebra, you'll need to address those separately. And remember, anytime that one factor is held constant, you can just get rid of it. That's it. Happy problem solving.